In this presentation, I am going to explain the previous GATE questions and answers for the year 2021, and the topic covered is analog electronics. Now let us see the first question of 2021 GATE question that carries 1 mark. First question. In the circuit shown, a 5 volt Zener diode is used to regulate the voltage across R0. This is a Zener voltage regulator, and this is the load resistance R0. The input is an unregulated DC voltage with minimum value of 6 volts and maximum value of 8 volts. The input voltage is minimum input voltage equal to 6 volt and the maximum voltage equal to 5 volts. And the value of RS is, that is this resistance, input side resistance RS is equal to 6 ohms. And the Zener diode has a maximum rated power dissipation of 2.5 volts. The maximum power dissipation of this Zener diode is equal to 2.5 watts. Assuming the Zener diode is ideal, the minimum value of R0 is how much ohm? This dash ohm. That is, what is the minimum value of the load resistance? That is R0. Minimum value of the R0 is the question. Now coming, this is a circuit diagram in which the input voltage is changing from 6 volt to the 8 volts, and the resistance series to the source, which is equal to Rs 6 ohms, and the Zener breakdown voltage equal to 5 volts, and this is the load resistance R0. And the question is that what is the minimum value of this R0? Now the load resistance minimum, that is corresponding to the minimum load resistance, the load current will be maximum. That is, if you select the minimum resistance, the load current is maximum. For the regulator to operate correctly, it must be able to supply the maximum load current even when the input voltage is lowest. That is, when the input voltage is equal to 6 volts, it should be able to supply the maximum load current. And we use the minimum input voltage for this calculation. That is why we are selecting the input voltage minimum value that is equal to 6 volt for this calculation. For the corresponding to the minimum input voltage of 6 volts, we are calculating what is the source current. IS is calculated. Therefore, 6 minus the Zener voltage equal to 5. 6 minus 5 divided by 6 ohm. That is IS minimum equal to, that is input voltage minimum value minus VZ divided by RS, or 6 minus 5 divided by 6 ohm. 1 by 6 amperes is the voltage current through this one corresponding to the minimum value of the input voltage. And that current is equal to the summation of the current through R0 or load current and the Zener current. And the load current is maximum when the Zener current is minimum, because the IS equal to, that is IS equal to Zener current plus the load current, and this Zener current, load current is maximum when Zener current equal to 0. That is, maximum load current occurs when the current through the Zener is minimum, or since we are assuming that the current through the Zener is negligibly small, or we are taking it as a 0, in that way we can say that the maximum current that can be flown through the R0, which is equal to this one, that is the current through IS corresponding to the minimum input voltage, and that is equal to, will be that is the for IL max is equal to this one, current through the source, from the source when the voltage is minimum, or that's equal to 1 by 6. For the maximum current through this one equal to 1 by 6 and the voltage equal to 5 volts. Therefore, the resistance or the minimum value of this R0, which is equal to the 5 volts divided by the resistance 5 volt divided by the current 1 by 6 amperes, which is equal to 30 ohms. Therefore, the answer is that is the minimum value of R0 is 30 ohm. Now let us see the second problem of 2021 GATE question that also carries 1 mark. In the BJT circuit shown, the beta value of PNP transistor is 100. Assume VB equal to minus 0.7. This is the circuit. And the voltage across RC will be 5 volts. Across this one, 5 volts. When R2 is, what is the value of the R2? That is in kilo ohms. Round off to 2 decimal places. Therefore, this is the circuit diagram in which the biasing voltage, that is equal to, this voltage is equal to 12, the VCC equal to 12 volts, and beta value of this transistor is equal to 100, and VB is given as 0.7, and the RC value is given as 3.3 kilo, and the voltage across this RC that is given in the problem as 5 volts. From that one we can calculate what is the this current, collector current IC, which is equal to 5 divided by RC, 5 divided by 3.3 into 10 raised to 3, or 1.51 milliampere is the collector current. And then we can find out what is the base current. Collector current, base current are related by IC by IB equal to beta, or IB equal to IC by beta, or 1.51 into 10 raised to minus 3, that divided by 100, or 1.51 into 10 raised to minus 5, that much milliampere, or that is the current. 1.51 divided by 100 milliampere is the base current, and this is 1.51 milliampere is the collector current. Now you can calculate what is the emitter current, or emitter current is the summation of the base current as well as collector current, or beta IB plus IB, or 1 plus beta times IB, or IE equal to 1 plus beta times IE, 1 plus 100 into 1.51 into 10 raised to minus 2 milliampere, or which is equal to 1.52 milliamperes. Emitter current equal to 1.52 milliamperes. And here R is given as, R is in the problem, it is given as 1.2 kilo ohms. Now we are going to apply the Kirchhoff's voltage law to this loop, whatever the shown here. No, we are going to apply the KVL to this loop, and our aim is to find out this voltage. What is the voltage at the base terminal? Therefore, we are writing the Kirchhoff's voltage law equation to this loop, which is equal to the input voltage equal to 12 volts. Therefore, 12, the drop across this one, minus IE into 1.2 into 1.2 kilo ohms. Then here minus, it is equal to 0.7, this voltage VBE, and minus here, which is equal to the drop. What is this voltage? What is the voltage means? Minus VR2. We have to find out the VR2 first. About minus VR2 equal to 0. Therefore, we are writing the Kirchhoff's voltage law equation to this loop. And in that case, we have to substitute what is the IE, which is already found at 1.52 milliamperes in this equation. And we can get the only unknown is the VR2. VR2 we can find out. From this equation, we can VR2 equal to 9.47 volts. The voltage at this point is equal to 9.47 volts. We'll be seeing in the next slide the continuation of this. Now continuing the same problem here, the same circuit as such, and we got the KVL equation for this loop, and solving that one we can get what is the voltage at the base terminal, or the voltage across R2. That's actually VR2, which is equal to 9.47 volts. Our question is that what is the value of the R2? In order to find out the value of the R2, we can calculate this is the current from the source to this point, which is equal to 12 minus the voltage source equal to 9.47 divided by 4.7 kilo ohm. That is equal to the input, this current I, capital I. And now already IB we calculated. So the total current through R2 equal to the summation of these two current. IR2 equal to whatever this current I plus the current IB, which is equal to 1.51 into 10 raised to. Therefore, the current through resistance R2 equal to 0.54, that is this current I, 0.54 milliamperes, plus base current. Base current equal to 1.51 into 10 to the power of minus 2, that much milliampere, or that is equal to 0.55 milliampere. Therefore, R2 can be calculated, this voltage divided by this current, or VR2 divided by AR2, 9.47 volts divided by 0.55 milliampere, which is equal to 17.21 kilo ohms. That is the value of the R2. Now let us see the third problem of 2021 gate question that carry 2 marks. A CMOS mid-trigger inverter has a low output level of 0 voltage and high output level of 5 voltage. And it has the input threshold of 1.6 volt and 2.4 volt. That is VLT equal to 1.6 volt and VUT equal to 2.4 volts and saturation voltage equal to 5 volts plus VSAT and minus VSAT equal to 0 voltage. The input capacitance and the output resistance of the Smith trigger, capacitance and input Smith trigger are negligible. The input capacitance not this one. Input capacitance of the Smith trigger and the output resistance of the Smith triggers are negligible. And the frequency of oscillation shown in the figure, question that what is the value of this? The frequency of the oscillation shown in the figure is how much is the frequency of oscillation for this one? That is the question, and that is to be round off to 2 decimal places in that one. And here the value of the C value is given, and the feedback path C and R are given, but the input capacitance and output resistance of the Smith trigger are negligible. Now to find out the frequency here, the capacitor voltage Vc and the output voltage V0 as shown in this figure. Therefore, this is the capacitor voltage, and this is called the lower threshold voltage, which is equal to 6 volts, and upper threshold voltage is equal to 1.6 volts, sorry, not 1.6 volts, and the upper threshold voltage equal to 2.4 volt. For this is the capacitor voltage, and this is the output voltage that is oscillating from the 5 volt and 0. For this time is marked as say T1, and this time is marked as T2, and the total time equal to T1 plus T2, which is equal to the total time period T, and the frequency of oscillation is given by 1 by T. And in order to find out the frequency of oscillation, we have to calculate what is T1 and what is T2. Then we can calculate T, and F is equal to 1 by T. Therefore, first we have to calculate what is the T1. And in order to calculate the T1 here the equation, basic equation of the capacitor, the RC circuit, in an RC circuit, the capacitor voltage equation can be written as here, that is initial value of the capacitor voltage to calculate here this one from this is the time corresponding to the discharging of the capacitor, and the initial voltage is equal to 2.4 volts. Therefore, Vc 0 minus equal to 2.4 volt, and this discharging that continues to, if as time t tends to infinity, this would have been gone to the 0, but when it reaches to the lower threshold voltage, again it is charging. Therefore, we can see that one Vc at infinity is equal to 0 voltage. And the question is that we have to write the equation corresponding to the capacitor voltage at any time t, which is equal to Vc at time t equal to the final value of that, or means that Vc at infinity plus Vc at initial voltage, Vc at 0 plus minus Vc at infinity into e raised to minus t by tau or t by Rc. Therefore, this is the equation for the capacitor discharge voltage at any time t. Therefore, substituting that one, we can get it as Vct equal to the, here we can set infinite, Vc at infinity is equal to 0 plus initial is equal to 2.4 volt plus 2.4 minus 0 into e raised to minus here t by Rc. For this equation during the discharging of the capacitor, that is Vct equal to, we can say it is equal to 0 plus 2.4 minus 0 into e raised to minus t by Rc. Or here at time t equal to t1, here at time t equal to t1 here, that is substituting that one here in this equation, the Vct is equal to 1.6 volts. At time t1 equal to capacitor voltage equal to 1.6 volts. Substituting that one here, 1.6 equal to here 2.4 into e raised to minus that time t1 divided by Rc, or t1 R and C are substituted, and here, and then we'll be getting the equation corresponding to this one. T1 is equal to Rc natural logarithm of 1.5. For this time is calculated, that is the discharge of capacitor from this 2.4 volt to 1.6 volt. That time it is notated as T1, and that is equal to Rc into natural logarithm of 1.5. Of course, the value of R and C will be substituting in the later. Already it is given R value and C value, that will be coming in the coming slides. Now continuing the same problem, 2021 gate question, and in that one, the previous slide we have seen, we have calculated this time, that is discharge of the capacitor voltage from this upper threshold voltage, that is 2.4 to the lower threshold voltage 1.6 volt, and we have calculated that T1. Now we have to calculate what is the T2, what is this time in which the capacitor is charging from say 1.6 voltage to 2.4 4 voltage. Therefore, at time t2 equal to VCT equal to the voltage that is at time t equal to 2.4 volts, or that indicates that 2.4 equal to here. In that case, we can substitute in that equation. Again, the capacitor voltage is equal to at any time equal to the VC at infinity plus VC at 0 minus VC at infinity e raised to minus t by RC. Same equation as we have seen here. And VC at infinity means this would have been gone. This is going up to the saturation voltage. This would have been gone to up to VC at sat, or that VC will be gone to up to the saturation voltage V sat. That is why VC t at infinity equal to taken as 5 volts. Therefore, and the initial voltage equal to 1.6. Therefore, 5 plus 1.6 minus 5 into e raised to minus t by RC. That is the equation for this capacitor voltage during the charging of that one. Therefore, now to find out the time t2 here, we're substituting the value of the t2. That is at t2, VCT equal to, it is equal to 2.4 volts. For 2.4 volts equal to 5 plus 1.6 minus 5 into e raised to minus t2 divided by RC. Or we can get it as e raised to minus t2 by RC equal to minus 2.6 divided by minus 3.4. Or we can get t2 is equal to RC natural logarithm of 1.307. Therefore, this is the time t2, and we can substitute the value of this R and C from this, that is 10 kilo ohm and C equal to 47 nanofarad, and can get what is the total time period t equal to t1 plus t2, which is equal to RC natural logarithm of 1.5 plus natural logarithm of 1.307. Therefore, I will be substituting this value of this RC, and then we can get what is the total time period equal to 316.4 microseconds, and the frequency of oscillation, that is this frequency is 1 by t, which is equal to 1 by 316.4 into 10 raised to minus 6, which is equal to 3160.55 hertz. Therefore, the frequency of oscillation of this Smith trigger, that is output voltage, that is equal to 3160.55 hertz. Now let us see the fourth problem of 2021 gate question that carry 2 marks. The fourth one is that the waveform shown in the solid line, that is actually this is one. This is the solid line. By clipping the full wave rectifier sinusoidal, showing the dashed one, the ratio of the RMS value of the full wave rectified waveform to the RMS value of the clipped waveform is how much? For we have to find out what is the RMS value of the full wave rectified waveform, and then you have to find out what is the RMS value of this clipped waveform, and what is the ratio of these RMS values. That is the question. Now, full wave rectified RMS value already we know it. I'm not deriving that one, which is equal to Vm divided by root 2. That is the RMS value of the full wave rectified output is, rectified waveform is equal to Vm divided by root 2, or which is nothing but 0.707 Vm. Now we are going to calculate what is the RMS value of the clipped waveform. For that one, RMS clipped waveform is equal to, what we are calculating is that we are calculating the RMS value from up to this pi by 2 here. Then 2 times that one we are just multiplying by 2. So instead of calculating from 0 to pi, we are calculating the RMS value from 0 to pi by 2. Then this is the one is the, of course, the image of mirror image of this one, so that we can multiply by 2 here. That is why I am doing this one. 2 times, that is 1 by pi integral 0 to this one. This is equal to pi by 4, since this voltage is equal to 0.707 Vm, and this is equal to marked as pi by 4. Pi by 4 to 0 to pi by 4, 0 to pi by 4 Vm square sin square omega t, plus from pi by 4 to pi by 2. From 0 pi by 2 to pi by 4 to pi by 2, 0.707. This clipping voltage equal to 0.707 Vm. 0.707 square Vm square d omega t, and that is the under square root. Therefore, this is the RMS value of this, the clipped waveform. Now, here it is equal to 2 Vm square divided by Vm is taken outside. So, 2 Vm square by pi into 0 to pi by 4 sin squared omega t d omega t plus pi by 4 to pi by 2 0.707 square d omega t under square root. Now again 2 Vm square divided by pi. Here sin squared omega t is written as 1 minus cos 2 omega t divided by 2, and integrating 0 to pi 4, 1 minus cos 2 omega t divided by 2 d omega t plus pi by 4 to pi by 2, 0.707 square d omega t under square root. The continuation will be in the next slide. Continuing the same problem, here we have to find out the RMS value of this clipped waveform, and it is equal to 2 Vm by square pi into half of omega t integrating, that is 0 to pi by 4, minus half sine 2 omega t divided by 2 into the 0 to pi by 4 plus 0.787 square omega t integrate to pi by 4 to pi by 2 all under square root. Or here 2 Vm by pi square divided by pi, half into, substituting here pi by 4 minus half into sine, you are substituting here, it is equal to sine 2 into pi by 4, sine pi by 2, and here also we can get it is equal to 1 by 2, which is equal to plus 0.707 square into, substituting here pi by 4 and all under square root. Again that is equal to 2 Vm by square divided by pi, which is equal to pi by 8 minus 1 by 4 plus 0.707 square into here pi by 4 under square root. Or again if you reduce it, that one, it is equal to under square root, this is Vm into, it is under square root 1 by 4 minus, substitute here 1 by pi into 0.707 square divided by 2 under square root, and we'll be getting it is equal to 0.584 Vm. For the RMS value of the clipped waveform is equal to 0.584 Vm, and the RMS value of the full wave rectified, already as I told you, it is equal to 0.707 Vm, or it's equal to Vm by root 2, which is equal to 0.707 Vm. The question is that what is this ratio, RMS value of the full wave rectified waveform to the RMS value of the clipped waveform. Therefore 0.707 Vm divided by 0.584 Vm, which is equal to 1.21. Therefore the answer is 1.21. Now as a generalized equation for any clipping voltage, I have explained in the previous slide, for a clipping voltage of 0.707 Vm. For any clipping voltage, you can remember this generalized equation so that you can find out the RMS value. That is, for example, for this clipping voltage equal to Vc, and this we have to find out what is theta c, and this is equal to pi minus theta c, and this is the generalized equation is that we have to find out what is theta c. For Vt equal to Vm sin theta, or clipping voltage equal to Vc, or we can say that Vm sin theta equal to Vc, or theta c equal to sin inverse, it is equal to Vc by Vm. First we have to find out what is this theta c, clipping the phase angle, or this phase angle corresponding to this instant at which the clipping voltage meets the voltage. For this point, what is the theta c? That is theta c equal to sin inverse Vc by Vm. Then we can substitute in this generalized equation, we can find out what is the RMS value of this clipped waveform, or clipped full wave rectified waveform. Therefore that is equal to square root of 2 by pi Vm square by pi, Vm square by 2 into theta c minus sin 2 theta c divided by 2 plus Vc squared into pi by 2 minus theta c under square root. Therefore if you remember this equation for any clipping voltage, you can find out what is the RMS value. Now let us see the fifth problem of 2021 gate question that carry 2 marks. A 100 Hz square wave switching between 0 voltage and 5 volts supplied to a CR or RC CR high pass filter, that is CR high pass filter is circuit as shown in the figure. The output voltage waveform across the resistor is, that is across this resistor, the peak to peak voltage equal to 6.2 volts. The peak to peak voltage across this one is equal to 6.2 volts. And if the resistance R equal to 820 ohms, C value is how much? That much microfarad. Round off to 2 decimal places. That is the question. Therefore, this is the high pass filter R and C, and the peak to peak voltage here equal to 6.2 voltage, and its input voltage frequency, or let's say square wave frequency, equal to 100 Hz, and the voltage is changing from 0 to 5, and from since it is 100 Hz, we can get that total time period is equal to, say, total 10 millisecond. Therefore 1 by 100, which is equal to 10 millisecond is the total time period. Therefore this period is equal to 5 millisecond, and this period is equal to again 5 millisecond. This is a 5 millisecond, then this one 5 millisecond to 10 millisecond. This is also 5 milliseconds. For that, this is the input voltage that is applied to the CR circuit or RC circuit. It's a high pass filter, and the peak to peak voltage equal to 6.2, and R value is given. You are asked to find out what is the value of the C. And from 0 to 5, the capacitor, that is from 0 to 5 millisecond, the capacitor will be charging through this one. The capacitor charges. And here, let us see that one, what is the capacitor voltage at time 5 milliseconds. In that one, the VC at the initial value, you can say that one, the initial voltage of the capacitor VC is 0 equal to 0. Since the capacitor is initially discharged, the initial value of the capacitor voltage is equal to 0. That's taken as 0. And the final value of the capacitor voltage here, the final value of the capacitor voltage is equal to, say, it is equal to 5 volt. It can charge you only up to 5 volts. So it can initial value equal to 0 and final value equal to 5 volts. Then we can find out what is the capacitor voltage at any time t. For VC at t equal to, as we have seen in the previous problems, it is equal to VC, the capacitor voltage at infinity, plus here initial value of the capacitor voltage minus the final value of the infinite value, the capacitor voltage at infinity into e raised to minus t by RC. So this is the equation to find out the capacitor voltage at any instant. Now coming to this one, at 5 millisecond, that is VC at 5 millisecond, the initial voltage is equal to 0 and final voltage equal to 5. For the 5 plus 0 minus 5 into e raised to minus t, t equal t by RC. T means this 5 milliseconds, 5 into 10 raised to minus 3, and RC, or the equation is equal to the, now the capacitor charging equation for VC equal to 5 into 1 minus e raised to minus 5 into 10 raised to minus 3 divided by RC. Therefore, during 0 to 5 millisecond, the capacitor voltage equation is given by this one. Or this is the voltage at 5 milliseconds, and the generalized equation is this one, the capacitor voltage at any instant. Now, since RC equal to the time constant equal to the RC, which is equal to from 0 to 5 volts, VCT equal to that, here VCT equal to 5 into e to the power of minus that, this is the t by 2, or this, that is this, from this at any instant, this one, the general equation during the charging equal to, it is equal to VCT equal to 5 into 1 minus e raised to minus t by 2, but at 5 millisecond it is equal to 5 into 1 minus e raised to 5 millisecond minus 5 millisecond divided by tau. Tau is the time constant product of R and C. Now continuation of the same problem. From 5 milliseconds to 10 milliseconds. Previously we have seen from 0 to 5 milliseconds. Now from 5 milliseconds to 10 milliseconds. Here the capacitor is discharging. The capacitor discharges from 5 milliseconds to the 10 milliseconds, and the peak to peak voltage across the resistor is given as 6.2 volt. That is given here, or that means that the voltage across the capacitor, the voltage across this resistor is changing from plus 3.1 volt to the minus 3. That is plus 3. This voltage is changing from here plus 3.1 volt to the minus 3.1 volt. For the voltage across the resistor VRT, which is equal to the input voltage minus the capacitor voltage. Input voltage is equal to, that is input voltage equal to 5 volts. 5 minus 5 into 1 minus e raised to t by tau. T is, that is meaning that 5 into e raised to minus t by tau. That is the voltage across the resistor. For the voltage across the resistor is shown here, that is changing from plus 3.1 to here minus 3.1. This is the voltage across this resistor. And the corresponding equation here is the change by 5 into e raised, the voltage across the 5 into e raised to minus t by tau. As such, here at 5 milliseconds, that is at 5 milliseconds, the corresponding voltage resistor or voltage across the resistor is given by, which is equal to this, that is changing to minus 3.1. At this instant, the voltage is changing to minus 3.1. For minus 3.1 equal to 5 into e raised to, that is minus 5 into 10 raised to minus 3 divided by RC. R is given as 820 into C. Therefore, here solving this equation, we can get the unknown C. The value of the capacitor C is given by 12.75 microfarad. For this, during discharge, the capacitor is discharging like this one, and the capacitor, here the voltage is changing at 5 millisecond to minus 3.1 voltage as such. Therefore, that is substituting here, we can find out what is the value of the capacitor C. So that is equal to 12.75 microfarad.